And I'm Sean Maxwell, so on behalf of ARMA and the Induced Seismicity Technical Committee, I'd like to welcome you to our monthly webinar series. So a series of webinars put on with our friends Jens Linsmead and Madi Haddad. It's been a very interesting webinar series. We've got some, as you'll see in a moment, some interesting speakers, topics coming up. Today's talk will be given by Heather DeShon with SMU, some very intriguing discussion on some of the insights and head scratchers, I guess, around the Fort Worth Basin seismicity sequences. So just before we get over to Heather and the main event, just a couple general announcements and housekeeping topics. So being part of ARMA, the American Rock Mechanics Association, the annual symposium is still scheduled for next June. We have a number of interesting sessions with the symposium. If you're not familiar with ARMA, I'd encourage you to go to the website. It's a great meeting, and this year being held in the Woodlands, north of Houston. It'll have, I'm sure, a strong petroleum or injection focus. And one of the sessions we have planned is on the topic of injection-induced seismicity. So the deadline for papers has been extended to November 10th. So if you have material, if you're interested, I'd encourage you to submit an abstract. With that, I'll pass it over to Jens to talk to our upcoming speakers.
Okay, thanks, Sean. I hope you can hear me. Let me know if not.
Yes, we can.
Yes, we have you know, as Sean said, we continue to add new speakers. We have Heather DeShon today, which I think we're all excited to hear from. Next on December 4th, same time, same place, Jamie Rich from Cimarex will be talking about the observations they've been making for microseismic induced earthquake measurements in the Anadarko Basin based on proprietary array data, I suspect, in that area. Following that, 8th of January, so this is not the first Friday of January to avoid the new year. The 8th of January, same time, 10 a.m. Central, Mike Brzezinski from Miami University, Ohio will be speaking, to be determined topic. Then Jake Walter a month after that from OGS, same time again.
Good morning and good evening, everybody. This is Mahdi Haddad from the Bureau of Economic Geology. It is a great honor to have all of you for another great induced seismicity webinar. First of all, I would like to bring up some of the rules that we have for better transition between different parts of this webinar. So everyone who has received the invitation email for this webinar will receive invitation emails for the upcoming webinar. So there is no need to request to be added to the invitation list for each webinar. Please do not forward the webinar invite. Instead, forward interested parties to the committee, me, Sean, or Yen, to be added to the distribution. So we would like to grow as an ARMA induced seismicity community. And so far we have had around 443 registered members that received these invitation emails that are almost equally divided between academia, industry, and regulatory agencies. Everyone will be muted during the talk for better hearing of the speaker. Please submit your questions during or after the talk in the chat button right at the bottom of the Zoom meeting window. Please send this question to everyone. And for your future reference, we record this Zoom meeting. Without further delay, let's invite Heather to have her talk. Thank you.
Thank you. I am really excited to give this talk, and I hope that we can have a really excellent discussion when it's all said and done. So if you give me a few seconds here to set things up on my side. All right. So today I'll be summarizing ongoing research of induced earthquakes in the Fort Worth Basin of Texas, located here. And I have organized this talk as a series of lessons and conundrums. Let's see why my slides are not. There we go. So I'm going to present about 5 lessons, and I'm going to present 5 conundrums. And I hope that at the end of the talk, we can discuss the conundrums, but I'm also happy to answer any questions about the lessons. So we're talking about the Fort Worth Basin, located in North Texas. This is in the Dallas-Fort Worth metropolitan area and beyond. The earthquakes in this area have been shown to be induced by wastewater disposal. So what I'm showing here is a picture of the basin. The colors represent kind of a simplified, spatially smoothed view of the waste fluids that have been injected into the primary storage formation, which we'll look at here in a minute. The squirrely symbols with the arrows are the wastewater injection wells. I've noted Dallas, where I'm located today, just for kind of a geographic point of view. And then the earthquakes are the orange circles. And what's being shown here are the North Texas Earthquake Catalog, or otherwise known as the SMU Earthquake Catalog for the basin. So there were no known earthquakes in this region prior to 2008. As you can probably already see from this figure, the earthquakes are spatially and temporally associated with the shale gas play, where the waste fluid disposal activities also take place. And if we take a step back and just look at the US Geological Survey's catalog, which captures all of the larger events, there have been about 35, a little bit more magnitude 3s since 2008, and only one magnitude 4 event, and that occurred in 2015 down here in Northeast Johnson County. So one nice thing, since this is a highly populated part of the United States, is that we have not seen the magnitudes of Oklahoma, nor the seismicity rates of Oklahoma. But that's also an opportunity, because we have seen individual fault sequences get activated, and they're spatially distant enough where we can put local seismic networks on top of them to look at just individual fault strands. All right, so let's look at the geology. I'm going to take a cross section shown here. All right, so the shale gas is extracted from the Barnett Shale, and that's this narrow orange formation on this stratigraphic section. And then the waste fluids are disposed into this thicker 1 kilometer thick unit called the Ellenburger. All right, and it's a karsted dolomitic limestone formation. In some areas of the basin, the deeper areas of the basin towards Dallas, there's another unit, the Viola-Simpson, that provides separation. And then out to the west, that Viola-Simpson disappears and separation doesn't exist. The Ellenburger lies unconformably on top of the crystalline basement structure. And most of the earthquakes in the basin, which I'll show here in a moment, do occur in that crystalline basement. And there is a regional fault system that we'll look at. Okay, so in my lab, we concentrate on high resolution earthquake location. We call our catalog the North Texas Earthquake Catalog. It combines early work from 2008 and 2009 by Brian Stump and Cliff Froelich, with more focused studies that have taken place since 2013. SMU operated 40 stations by 2016 in the Fort Worth Basin. And then the Texas Seismic Network went online in January of 2017. And there are still combined between SMU and TexNet about 40 stations in the Fort Worth Basin. All right, so here's just a station map and an earthquake map. And you may notice right away that the station map actually reflects the earthquakes. And this is an important point to always remember about the SMU catalog, is that we deploy in response to felt earthquakes. That means that the larger felt events are always in only the USGS catalog, and the SMU catalog reflects earthquakes that occurred after the seismic networks were put into place. So we call these local research seismic networks. All right, and again, TexNet is now operational. This is a unique and important resource for the state of Texas. The TexNet design goal is to reduce sensitivity across the state to magnitude 1.5. And then this is to complement and build upon the US Geological Surveys catalog, which in Texas has a magnitude of completeness around magnitude 2.7. All right, and then temporary networks like SMU's networks expand and allow further detail into basins of interest. So the Fort Worth Basin has 5 named earthquake sequences. So the first 2 named earthquake sequences resulted in local research seismic networks being put in place by Brian Stump and others at SMU. All right, and that's the DFW Airport earthquake sequence in 2008 and the 2009 Cleburne earthquake sequences. All right, then in 2013, beginning with the Azle Reno sequence outside of Fort Worth, we have built up more, we've built up the seismic network, and we've recorded to greater resolution the Irving Dallas earthquake sequence and this ongoing earthquake sequence in Northeast Johnson County. All right, and the cross sections here are just showing you the catalog for Azle, Irving Dallas, and Northeast Johnson County or Venus. And again, this is just to reemphasize that most of the earthquakes occur in the basement, though some earthquakes in the Azle area do appear to occur in the Ellenburger itself. All right. The 5 sequences are named because SMU and our collaborators placed seismic networks on top of them, but there are many other source zones in the Fort Worth Basin. All right, here I'm showing 3 that have occurred in the 2018 time period. Another outside of Cleburne, a fault strand that became active outside of Fort Worth, and then up near Lake Louisville. Now, in all of these cases, by the time SMU put seismometers on top of the sequences seismicity rates had decreased significantly. And so you can see when we don't have a seismometer on top of these very small earthquake sequences, our depth resolution is really terrible. All right, so I'm showing cross sections, but that's actually to show you that our depth resolution is quite poor and varies from where we have 5 seismic stations or more to where we are operating kind of more regionally. All right, so in this basin, we do seem to have swarms or clusters of events that are mixed with more traditional main shock aftershock sequences or earthquake interaction. And this is just showing you magnitude over time. Again, to re-emphasize that there are a number of earthquake catalogs available to study Fort Worth Basin earthquakes, not just the SMU catalog, but also to re-emphasize that the SMU earthquake catalog is variable resolution in space and time, and that some of the larger earthquakes are in fact in the US Geological Surveys catalog, but not necessarily in the SMU earthquake catalog. All right, so anytime you have earthquakes, you have some background information you need to establish. So Jens Ledsny and Mark Zobak gathered data to establish SH max or stress in the overlying sedimentary units for the basin, and that's what's being shown here by the red bars. And then with our earthquake catalog, we can also generate focal mechanisms. And here I just want to emphasize that most of the earthquakes in the basin are occurring on steeply dipping normal faults, and that a stress inversion of the focal mechanisms yields maximum stress in the basement, striking 20 degrees to 25 degrees east of north, and entirely consistent with the SH max information derived from the sedimentary units above. All right, so lesson number 1. Let's look at the faults. The faults can be viewed using seismic reflection data. A lot of the seismic reflection data is proprietary. Some of the 3D seismic data was made available to Beatrice Magnani at SMU, so I'm going to focus on that work. And what you can see from her analysis is that the faults connect the units of interest. In other words, they connect the Ellenburger to the basement. And most importantly, they haven't appreciably deformed materials younger than about 300 million years in this area, right? So they don't go to the surface, and they are an old pre-existing fault system that becomes denser. The fault spacing becomes less as you approach the edge of the, or where the Awatch-Tuth thrust comes up and over the basin. All right, so the seismogenic faults in this case look identical to many neighboring faults that have not hosted seismicity while SMU has been recording. So this is from Irving, Dallas. These faults are clear in the 3D seismic reflection data for this area. The Irving, Dallas earthquakes themselves occur on a fault that parallels but is just off of the boundary of this particular 3D seismic survey. All right, so lesson 2, how do you build a fault map? Okay, so Peter Henning's group down at the University of Texas has gathered all available public and some industry data as they can to start building up a map of faulting in the basement of the Fort Worth Basin, and that's what's being shown on this map. Also being shown by the colors are fault slip potential calculations. All right, so if you assume 1 megapascal of pore pressure increase, what the colors represent is, or what the colors show is faults that are near critically stressed in the modern stress regime under that pore pressure increase assumption. All right. So it looks like most of our northeast southwest trending normal faults in this region are actually near critically stressed in the modern stress regime. All right, but why do some but not all of these faults slip? In fact, if you look at this map in great detail, you can see northeast southwest trending faults with higher fault slip potential that don't slip, but are near moderate to for Fort Worth Basin high volume injection wells. You can also see north-south oriented faults with low fault slip potential, or this is actually a north-south oriented fault with low fault slip potential that did generate earthquakes all the way back in 2009. I've already shown you faults in the seismic reflection data that look identical to neighboring faults that have hosted earthquakes, but have not themselves hosted earthquakes. And then we also see some faults that host a handful of events, right? Like Lake Louisville, or maybe this Fort Worth Basin fault, or this Fort Worth fault. But then we have one area, Northeast Johnson County, where the seismicity has been going on for over 10 years. All right. So originally, there were when the transportable array came through, Cliff Froelich did a nice study looking at earthquakes in the Fort Worth Basin, and those earthquakes tended to occur near moderate to high volume injection wells. So that speaks toward a mitigation strategy, a potential mitigation strategy, right? However, as injection has continued across the basin, the earthquakes have spread out in time. So what I'm showing here is just, again, a simple spatially smooth version of injection volume for 2008 to 2010. And here's one for 2014 to 2018. Just to reemphasize that the earthquakes have spread out across the basin, again, occurring on pre-existing faults, and tend to be occurring in areas where pore fluid pressure would have been expected to increase, but not in Dallas Irving. So this is going to be one of our big conundrums. What triggers the Dallas Irving earthquake sequence? All right. So what I'm calling lesson 2 is that there's no clear and easily quantified predictive relationship between earthquakes and injection. So maximum injection occurred in 2012. The largest earthquakes and the highest seismicity rates occurred in the 2014 to 2016 area, right? So there's a lag. We would expect to see a lag. Back in 2017, we went to see if there was some quantifiable relationship between the summation of seismic moment versus cumulative volume, for example, and we didn't see anything, right? So this is the Irving earthquake sequence, the Azle earthquake sequence, and the Venus earthquake sequences cumulative seismic moment plotted against the cumulative volume of their nearest injection wells. For Irving, we had to go out 15 to 20 kilometers to get an injection well. All right. This was back in 2017. There have been no bigger really earthquakes since then. The volumes have, injection has continued, but the volumes haven't really gone up or been high. So this relationship that I'm showing here, while dated, would still largely hold, right? It's not up with the little yellow dots, other induced significant earthquake sequences. All right, so let's think about stress change, right? How much stress change is necessary to induce the first earthquake, right? I don't really like this question, in part because we know from aftershock sequences, what I'm showing here is just an aftershock sequence in California. We know that on critically stressed faults, when they're perturbed by, say, a larger earthquake, aftershocks occur under really small stress changes. Okay, so what really is our realistic expectation for stress change in the Fort Worth Basin? Well, let's at least think about what has gone on in the Ellenburger since 2012. Now, fall-off tests are fairly rare. After the 2015 Venus earthquake, for example, the nearby wells were shut down, and how that system perturbs after the shutdown will actually give you some indication of the pressure in the Ellenburger, or at the base of that injection well. And the fall-off data, or the fall-off testing data from the Venus area in 2015 suggested that the Ellenburger was overpressured at that time above hydrostatic, anywhere between 0.9 and 4.8 megapascals. Now this, all right. At SMU, we've done pore fluid pressure modeling, diffusion modeling, and we consistently see really small values. So this modeling was done by Paul Aguirre. It's looking at the Dallas-Fort Worth airport sequence in 2008, where injection begins at what we call the south well, and earthquakes occur soon thereafter. Injection begins at the south well. Now, Paul has modeled here pressure increase in the basement, not in the Ellenburger, under, of course, some assumptions about fault permeability and fault thickness, but he sees, or he sees an estimated pressure change only on the order of about 0.2 megapascals. These values are actually very similar to the first pore fluid pressure diffusion study that we produced at SMU, and this was Matt Hornbach's modeling results for the Azle earthquake sequence. All right, and again, these were fairly straightforward, simplified models looking only at pore fluid pressure diffusion, but we saw anywhere between very little to 0.4 megapascals of change develop along the fault within the Ellenburger. But we did report significant pressure differentials when you actually tried to consider the effects of the production wells in this area. All right, so lesson 3 is simply that it appears that very small pore fluid pressure changes could trigger the initial earthquakes. Now, I know there are people out there thinking, yeah, but what about poroelasticity? Okay, and that goes back to this question. Let's ask a different question. What type of stress change and what kind of slip is necessary to induce the first earthquakes on these faults? All right, so Zhai and Sherazai in 2018 did a really nice study looking at both pore pressure diffusion, poroelasticity, and Coulomb stress changes across the basin. All right, and they cut off in December 2015 because you have to stop looking at injection data at some point. All right, the results look kind of similar to those figures where I was just smoothly plotting total injection volume, right? The earthquakes occur in areas where pressure or stress has been modeled to have increased over time, except for the Irving Dallas earthquake sequence. All right, you have to remember at the airport, the well was almost right on the fault. And so even though it looks like the airport itself is not in an area of pore fluid pressure change, the injection was literally almost right on top of that fault. All right, so I want to also ask some questions that I don't think the Fort Worth Basin data set is going to allow me to answer. What if there's aseismic slip on these faults? How would we be able to tell with the earthquake catalog we have in the Fort Worth Basin? If there is aseismic slip, what is the balance between seismic and aseismic slip? So these are the sorts of questions that I would that I follow from the literature in other basins, and that I wish we could address in the Fort Worth Basin. All right, one thing we can do in the Fort Worth Basin now, thanks to primarily some of the efforts down at the TexNet Scissor Group down at the University of Texas and collaborators, is we can start building 3-dimensional models that reflect the best geology, the best geophysics, and the best geomechanics information. Now I'm biased. I'm showing the results from my own student, Luis Quinones here. These are models developed in COMSOL multiphysics, and we're really targeting this Irving Dallas earthquake sequence, right? There's really no nearby injectors. The closest injectors are really not even very high volume. Why did this sequence occur? All right, and so this is just a snapshot of his results, but the Irving Dallas earthquakes are blue, right? So again, even when we look at pore fluid pressure diffusion, when we look at how or if the faults themselves are serving as pathways for transferring stress up into the Irving Dallas area, north into the Irving Dallas area, we are still seeing very small changes on the order of 0.2 or less megapascals. So this modeling itself raises all sorts of questions, right? You can put all this data into these models to better explore physical mechanism, but we get kind of stymied, right? What is the relevant fault density, right? We see where we have 3D seismic data that there's lots of little faults. But then when we don't have 3D seismic data available to us, the fault maps have these only the larger faults, right? So we're a little limited by data availability. What's the permeability of these faults? These faults are 300 million years old. At some point, they were active faults with damage zones, right? What has happened to those damage zones? Is it important to know what has happened to those damage zones, right? What fault width should you be putting into these complex three-dimensional models, because it really does affect the absolute values of stress changes that come out of these models. All right, is there significant compartmentalization going on in the Fort Worth Basin? Right, there's actually a strip in the Fort Worth Basin where there doesn't seem to be any faults, right? And there's actually not many earthquakes up that strip. So how is that type of compartmentalization affecting what we're seeing in the earthquakes? All right, ultimately, we're doing all of this in order to understand hazard, right? So some conundrums here are, how much strain is really left on these faults, right? Or are we releasing newly accumulated strain? And then what are we going to do? What is the hazard and risk associated with Irving, Dallas, which sits under a city that I love, right? Under Dallas. All right, so we looked at stress drop. The stress drops we find in the Fort Worth Basin are consistent with intraplate earthquakes. Okay, we're going to skip the quote. There's one exception, and that's the airport. Again, where the injection well was really quite close to the fault that gets activated. The airport earthquakes actually have low stress drop. All right, so here are the airport earthquakes in red. For events within 1.5 kilometers of that injection well, early on in that earthquake sequence, we actually see low stress drop. All right, so that suggests to us that perhaps low stress drop can be used to explore cause. But in the Fort Worth Basin, it's only in a very specific case where the well and fault separation was very small, and where we had high quality local seismic stations, where we captured the low stress drops that might actually directly reflect pore fluid pressure change at the source. All right, if we just take our bulk average for a stress drop in the Fort Worth Basin, and pair that with the fault length information from Peter Henning's group and place that on a scaling magnitude versus fault size map, it looks like some of these faults, if they had failed in a single earthquake, could have been a little larger, right? Nearer to magnitude 5, where you might expect to start to see damage in a built environment like Dallas from an earthquake of that size. But it's important to stress that multiple events are more common. We've never had a traditional main shock aftershock sequence in the Fort Worth Basin where the largest earthquake occurs with maybe just a few foreshocks. And you would maybe think about actually slipping on the entire fault length. All right, so I hope I've convinced you that the cumulative history of wastewater injection and even fluid production within the Ellenburger and the evolution of pressure and stress in this system is what is driving our earthquakes now. And we still need to think about what are the best mitigation strategies. And we also need to think about how do we recognize when the hazard is returned to background, right? If background was 0, when do we say that we're back to background? All right, so I'm going to skip this for time. Oh, actually, no, because I set my timer at 30 minutes. All right, so my 5 lessons, right? These are old pre-existing faults, right? They've not appreciably deformed materials younger than 300 million years. They do appear near critically stressed in the modern stress regime, but we have instances where faults that don't appear well oriented in the modern stress regime have generated earthquakes, and we have instances where faults that probably or you think would have maybe had earthquakes have not had earthquakes, right? We don't want earthquakes, so that's fine. There's no clear and easily quantified predictive relationship for earthquakes and injection volumes or rates in the Fort Worth Basin. I've given talks in other places where I go in great detail through each earthquake sequence and show you that they all 5 of them have really unique time and space history relationships with their nearest injectors. Very small stress changes appear to feasibly trigger the initial earthquakes. At some point, there are earthquakes with their own aftershock sequences buried in all of our earthquake sequences, right? So that's why I always concentrate on what was that first, what started the earthquake sequence. The injection-induced earthquakes appear to be releasing pre-existing strain, or if you want to call that natural tectonic stresses, with the exception, of course, of the first earthquakes of the Dallas-Fort Worth airport sequence. And I do think the cumulative history in injection and production has to be tracked over the life cycle of a basin. So when you start to go into a new area, this is recording the earthquakes, or recording in case there are earthquakes, is something that should be kept in mind, and also collecting maybe more data than you think you should at your injection well and even your production wells. So the conundrums: why do some but not all of these faults slip, right? How much strain is really left on these faults? What type of stress changes and what kind of slip is most important to constrain or actually trigger the first earthquakes? With these complex 3-dimensional velocity models that we're using to explore physical mechanism, what is the most important data that we need to gather to constrain the hydrogeologic or the geomechanical or geophysical models? The Dallas-Fort Worth earthquake sequence remains an enigma to me in some respects, and how we recognize when the hazard is back to background, other than saying when there's no earthquakes, is a question. And what are the best mitigation strategies? And by that, I mean beyond inject less or at lower rates, or right, thinking a little more in detail on that question. We're still missing key data, especially in Texas, right? I would like to see monthly data. I used to say daily, but honestly, with COVID, if you gave me daily data, I probably wouldn't look at it for over a month, right? So, but we need data more than once a year. Time and space correlation is not sufficient to understand physical processes. We need to track local and regional subsurface pressure changes in both space and time. Daily or monthly injection, you should be at least gathering daily injection data, even if you only have to report it monthly. Downhole pressure and fall off tests really do provide important information, even though that means a well is offline for a few days. It's just fundamental, so fundamental. Fluid production information, properties of the fluids, not just what comes out, but what went in. There was that really interesting Virginia Tech study that I would point you to if you hadn't read that. All right, so we need to integrate geology, fault information, catalogs, modeling efforts with timely data, okay? Injection data, and we need to monitor over the full cycle of a system. So even if the earthquakes are really small and you think that, well, if people aren't feeling them, they don't matter, I don't think that's true. I think the little earthquakes do matter, right? You need to be capturing the full life cycle of the system if we really want to key in on what is most important. All right, so thank you very much, and I hope we get to have an excellent discussion.
Great, thanks, Heather. Very, very interesting presentation. A lot of material, a lot of good and intriguing points you brought up. So there's a number of questions on the chat. I'd encourage everyone to add to the list, but I'm going to start with a question from David Eaton. He asked, looking at the fault structure, if there's any tendency for the faults with more throw to be more seismogenic, or actually you worded it less throw to be more seismogenic, but maybe just to generalize, do you think there's any association between the throw and the faults and the seismogenic potential?
There. I'm just trying to get the chat up just a second. So that's a good question. The fault with the largest throw that I know of in the system, and if Peter Hennings is on, he might be able to correct me, but the fault with the largest throw is that airport fault. All right, the fault that generated the original 2008 Dallas-Fort Worth airport earthquakes. And interestingly, those earthquakes are not anywhere near the highest magnitude. So from the seismic reflection data, it doesn't look like there's a correlation between earthquake throw based on what was happening hundreds of millions of years ago and the size of the earthquakes that have been induced.
Okay, great. And Dave has a comment here, but before we go to the comment, I guess I was going to ask a question myself. Look, when you showed the focal mechanism, it was striking how a number of the clusters were almost identical mechanism, but Azle seemed to be the exception where there's much more scatter. Any comments there? Is that reflecting changing in the local fault structure? Or?
Okay, yes. So that's a good catch. This is actually something that we discussed in the paper that figure came from, but I had removed those words. So it is, in my opinion, that one of the interesting aspects of the Dallas-Fort Worth or the North Texas earthquakes is that the fault mechanisms are incredibly similar. All right. And I like to speculate. Now, people at SMU argue with me about this, but I like to speculate that the lack of variability in the focal mechanisms means that the old damage zones haven't been reactivated. Azle, the focal mechanism quality is unfortunately reflective of the network quality. When the Azle earthquakes happened, we received netquake stations to put into place, and then a major ice storm hit, and it made us miss some larger earthquakes, but it also meant that we started with these netquake stations, and then we kind of threw out anything we had in the basement of SMU, and we moved things around. And so the actual graded quality of the focal mechanisms in Azle is not as good as Irving, Dallas, and Northeast Johnson County. Also, the stress field starts to rotate a little bit as you move out towards Azle, and so that can change the, that seems to also be reflected in the focal mechanisms out in Azle.
So Peter Hennings just added something to the chat that he sent you the figure to answer Dave Eaton's question.
I'm gonna have to open my email and log in though, because I didn't want it to bing at me while I was talking.
Yeah, no problem.
So we might have to answer Dave's question via email afterwards.
Or maybe a follow-up presentation. We can we can have a three-way panel to discuss structure.
Well, I can look on my phone real quick.
Well,
but you can go on.
Sure. So Dave also has a comment here about, it's actually a good segue from your comment a moment ago, Heather, talking about the damage zone. And so Dave's comment is whether or not there could be activation of the damage zone as opposed to the fault itself. And to me, it kind of talks to what is the damage zone? It seems that Dave's kind of alluding to the fact that the damage zone is going to be comprised of fault segments or structure in a different orientation from the main fault itself. And that certainly reflects on something that we often see in Anadarko Basin in Oklahoma, for instance. There's kind of major regional structures that create secondary structures that become seismogenically active. But so Dave stated as a comment, but you can treat it as a question too. Heather, what do you think of the nature of what is the damage zone, perhaps a good way to phrase it?
I have to admit that I probably have a simplified gut instinct vision of what the damage zone is, just based, primarily based on what damage zones look like in the geologic record, right? So that they, get the damage zones host or get quite complex and larger, right? The older and more active the fault has been over time. And there should be all these subsidiary structures within the damage zone that during main shock aftershock sequence lead to this variability in focal mechanisms, for example. And then they should heal, right? Like when you look at what they look like in the geologic record, they begin to heal. And then the way I think of it is, okay, so what materials are now, what are the actual minerals and rock there on that old fault, right? How are the injected fluids and the resulting pore fluid pressure that's diffusing away for those injectors, are they moving differently through those materials that are now that old damage zone than the surrounding rock, right? And how can we capture if that's occurring? So I'm sure I didn't answer his question at all, right? But these are just these are questions I have. This is just how I think about it. I kind of wish everybody else could be unmuted so I could hear how you all think about it.
So Dave kind of teed it up as a comment, and I think I tried to transition it to a question, but maybe it's something we don't know the answer to. It's more commentary, and so maybe we'll continue on. It seems like an intriguing question. What is the damage zone? So Mike Wood asked a question. So first of all, he states how much he enjoyed the talk and the material. So I'm sure it's echoed by all the attendees. But he also asked a question of, as you're putting in the temporary networks and changing the sensitivity, you kind of alluded to that a number of times. In terms of the question of getting back to background, I think his question is, what is background? And can we really define what that is?
Yeah, right. I mean, okay, so background is limited by the sensitivity of the networks, obviously. So the, USGS at above magnitude 3 in a highly populated area like the Fort Worth Basin would have reported something. And in fact, what we could, right? Cliff and collaborators at the Dallas Morning News and Matt, really the collaborators at the Dallas Morning News, they went back through their records back to the late 1800s just to see what they had reported, right? They reported that Miss So-and-so's cat ran away last night, but they didn't report anyone feeling any earthquakes that would appear to have been within the Fort Worth Basin. That's what we know. that's what we know. We know that there have been no magnitude 3s, and we know that there have been no people talking about feeling anything like earthquake shaking that made it into any of the newspapers since the area became relatively populated.
So I'm going to be Canadian, and I'll apologize for the unanswerable questions we group. Hopefully the next one is answerable. So it's from Cameron Karimi. He's asking, so you talked about trying to correlate pressure, Coulomb stress changes, et cetera, with the parameters with the seismic activity, and he's asking which one shows the best correlation, the strongest correlation.
So I would have to go back to the Zai and Sherzai paper. To my mind, at the scale of the basin, they all seem to give about the same answer. In fact, we've been looking, so JP Nico and Rebecca Gao have a really interesting study that's in review, looking, putting together a hydrogeologic model for the Fort Worth Basin. And their model for the Dallas Irving earthquake sequence also predicts or suggests these really low stress changes. There's some work out of Peter Eichenbull's group at the BEG that really makes sure that poroelasticity is being included. And I think we all still debate in the Fort Worth Basin what's really more important, pore pressure diffusion or poroelasticity. We do know that, like, if you just take the magnitude 4 and do a bulk Coulomb stress change, that sort of Coulomb stress change doesn't actually make it all the way up to the Dallas Irving earthquake sequence. So again, I'm not sure that I have a specific answer to that question.
Then again, I'll be Canadian and I'll apologize for that.
Apologize.
Yeah. So Peter Hennings has posted, I think, the picture to the chat window. Peter, can you, I couldn't do it, but Peter, if you could unmute yourself, and if possible, if you want to share your screen, you'd be, if you've got the answers.
Just have a check and see.
Hi there. I don't have the answers, and we have several different people with meetings in my office right now, so I'm sorry about the noise, but let me try to share my screen. Let's see if this will work. Yeah, here we go. So Dave, great question.
Yeah.
And let's see what happened. It's not sharing. Is it sharing?
Yeah, I can see it, Peter.
Okay.
Yes, sir.
So this is just a standard, fault length versus throw plot from the paper that Heather discussed, the fault characterization paper. And it shows the different data types, faults from 3D seismic, faults from 2D seismic, and mapping horizontal wells and whatnot. So the black boxes are the faults that in our fault interpretation and with Heather's earthquakes, we nominate as being the seismogenic faults. And so you can see where those faults sit in terms of their length, generally less than 10 kilometers in trace length, and then with throws that are almost exclusively under 100 meters of throw, which would be calculated at the top of the Ellenburger or the top of the basement level. That one fault that Heather mentioned, the DFW airport fault, is the outlier, which is considerably longer in that log scale than the other seismogenic faults, and has up to perhaps a couple of 100 meters of throw. So we see that the distribution of faults in their length and throw character is about the same distribution as the fault population as a whole. So we don't draw any conclusions about something special with regard to the scaling and the seismic potential, I would say. The potential for a fault to have ruptured. Of course, the energy release is a different topic that I'm not prepared to talk about. But so I hope that answers Dave's question.
Great, thanks, Peter. And if you wouldn't mind, could you put the reference to that paper in the, if others are interested in following up?
Yeah, for sure. Yeah, I'll put it in the chat.
Great, appreciate it.
Let's see. So how do I unshare here before something unpleasant happens?
Yeah, it's harder to unshare than you think, especially if you have that laser pointer turned on.
Yeah. Well, Heather, why don't you share back, and that'll get me off the hook.
I think you're off now, Peter.
Oh, you're off now, Peter.
All right, thanks.
So I guess just a few minutes left, but maybe I'll take the opportunity to ask the final question. And Heather, it goes back to a conversation we were having before the webinar started about aseismic slip. And I think you referred to it a couple of times, referred back a couple of times during your presentation. I was curious, you were talking about trying to identify aseismic slip within the seismic catalog, which sounds like a difficult task in itself. But I was wondering if you looked at INSAR, or any of your group might have looked at something like INSAR that might complement.
Yeah, so we have. Again, we're thankfully, because it's a highly populated area, we are thankfully limited by the fact that our largest earthquake is a magnitude 4. And we are also limited by when our earthquakes happened relative to when INSAR satellites were up, right? So, or when the satellites were passing over North Texas. So Zhang has at SMU is an INSAR specialist. He has definitely, every student in here that's taken classes from him have looked for INSAR deformation and in the Fort Worth Basin, and we have never successfully resolved deformation using INSAR techniques. Where I'm thinking is, and it's in part based on Elizabeth's talk, is that we've never really done a good template matched earthquake catalog for the entire Fort Worth Basin. I hope to have that done by EGU, but the High Performance Computing Center at SMU is under high load right now, so I don't know if it'll get done. But a lot of times repeating earthquakes and these ideas that Elizabeth and Thomas Goebel and that come out of the Southern California studies of earthquake clustering might be able to shed some insight on that. And so doing a more careful study of repeating earthquakes and earthquake clusters versus foreshock, mainshock, aftershock sequences is something that still needs to be done in the basin. But again, we're always limited by what we were able to get in our earthquake catalog in the Fort Worth Basin. And there might be other better earthquake data sets out there to explore these ideas than ours.
Great. Well, this pretty much brings us to the end of the scheduled hour period. So on behalf of everyone, Heather, thank you for the sharing the lessons and the conundrums, the very intriguing presentation. I'll remind everyone our next presentation is the first Friday in December. The date escapes me, but the speaker is going to be Jamie Rich with Cimerex. So it'll be interesting to get a representative of an operating company to talk about kind of the industry view of induced seismicity. So thank you everyone for attending, and watch out for the meeting invites. And again, thank you, Heather. We have a tendency, people often stay on and ask questions. And again, Heather, it's really up to you if you want, how long you want to continue answering questions. But if anybody has questions, feel free to unmute and make this more of a conversation. Thank you, everyone.
Well, thank you all for coming.
Thank
and
you.
I can stay on for a few minutes for sure.
Thank you so much, Heather.
You're welcome, Mari.
So Alexandros has some comment about the damage zone. He has written that I think Dave's reference to damage zone is the flower structure we have in a fault, that the shallow part in the damage zone being active sometimes without the deeper fault being active.
Yeah, so
just Heather, let me jump into this. I think that Dave is referring to some this type of fault structure that is pretty common, that when we have the shallow part of the fault that has been activated, but not the deeper part. But I think in your slides, you haven't seen, you haven't presented something like that. You have presented cases, yes, that you have the seismicity going through the whole, from top to bottom, let's say, of the fault.
yeah, I mean, so Beatrice and I have looked at earthquakes on flower structures and earthquakes on the shallower portions of New Madrid faults before, because those are the New Madrid intraplate faults, right? They're two strike slip systems with a reverse fault on the step over. And, you know, those faults in New Madrid, those strike slip faults, they have like really nice flower structures that you can see in the seismic reflection data down the Mississippi River that Beatrice collected. And there you do see, you know, a lot of earthquakes on the shallowest portions and then the bigger earthquakes. And, you know, in the intraplate New Madrid system, those earthquakes go much deeper than anything we've seen. So my assumption here in the Fort Worth Basin on these normal faults is that in fact, the induced earthquakes are occurring on the shallower portion of the system, and that those faults themselves probably do extend much deeper, and we haven't, but we never really see earthquakes above or below 10 kilometers here, whereas in the natural system, the Madrid system, right, you see earthquakes down to like 20 kilometers depth. So that's interesting. And then we, you know, these normal faults, we don't really have, to my knowledge, of flower structure. We have seen the antithetic fault in Azle, but the antithetic fault in Azle could actually just be related to the edge of a large karsted pipe system in that region. The pipe karsts out in the Azle area are quite large. Karst pipes. Listen to me doing poorly with my geologic terminology.
Hey, Heather, I was thinking also, if anybody attended GSA last week, there was a couple of good talks about the basement geology, and at least one by Fola Kolawale from formerly from University of Oklahoma, characterizing the basement, at least strike slip faults in Southwest Oklahoma. I don't know if that's relevant, but there are scaling relationships in addition to that, of course, that might be useful for understanding the width of these zones relative to the size of the main fault.
I think you're muted, Heather.
Oh, I am. A lot of Peter's group's fault information actually comes from exposure of the faults in the Ellenburger down outside of Austin, right? So nowhere near Dallas. So I think it's always important to return to what the geology where those systems actually come up is exposed, and you learn important information from that. Then you have to extrapolate how that would change as these things are buried, but you have to look at the geology, says the seismologist.
I have another question here on that. But when since the injection is on the deeper layers, so you wouldn't expect that the earthquakes will be also as it is on the deeper part of the fault. So there wouldn't be a case where the fault will be active only on the shallow part, but also will be active on the deeper part. Correct?
Yeah, I mean, I agree. Again, it might be simplistic, but when I think about the pore, and again, I probably think too much about the pore fluid pressure diffusion and maybe not enough about the poroelastic effects. But when I think about the pore fluid pressure diffusing and reaching a fault and then using some, but not all faults as some pathway to get a stress change into the basement, it's natural for me to think that that stress change has to be higher nearer the top of, or nearer where the fault, where the basement Ellenburger intersects, and then decreases with depth, which might well explain why the seismicity rates appear to be higher near the Ellenburger basement intersection. But then, of course, the strain to be released is obviously perhaps higher the deeper you go. And so we do think we see the larger earthquakes occurring a little bit deeper into the system. But in Azle, we see these little pockets where there's like a high seismicity rate right along the top of the Ellenburger basement intercept, or where those two things meet. And then, of course, we missed capturing the larger earthquakes, and the US Geological Survey's depth resolution is really very poor and in space for the Azle earthquake sequence. So it's always, we're always trying to figure out for like the 3 events we captured that were magnitude 3s, like were they deeper on the fault than all of these tiny little ones that we've seen up closer to the boundary. We're always limited because we respond instead of just had the ability to set something out and wait.
All right, does anybody online have any other comments or questions? Alexandra just gave you a big thumbs up, Heather, I see.
Thank you, Alexandra.
I saw lots of clapping emojis as well.
I have the grid view up now. All right, well, I'm looking forward to the next 3 talks. So thank you all for coming.
Thanks again, Heather. Have a good day.
You too.
Thank you so much for having this talk.
You're welcome.